Dear friends and followers, welcome back to my channel, and in this video I'm going to show you how to simulate a microstrip line in HFSS. So in order to simulate a structure in HFSS, the first step is to make that structure in an HFSS environment. And this includes assigning the material properties, defining the boundary conditions, defining the ports and reference plane, and making the simulation box around the object that you want to simulate. And then after that, you have to set the simulation properties. For example, if you want to simulate it from 1 gigahertz to 5 gigahertz or 2 gigahertz to 10 gigahertz, and also the steps of simulation. And then after that, we can simulate the structure. The next step is to validate the results. So we have to check the results to see if they make sense by checking the S parameters or current density in different parts of the object. And in this video, we'll see that how to export the results from HFSS into ADS in order to compare the results between these two softwares. So at the end of the video, you will get familiar with how to make a microstrip structure like this in HFSS, and at the end, we see how we can plot the results in XY plane, the frequency domain, or on the Smith chart. So this is the microstrip structure that we designed in the previous video, and the link to that video is in the description box below. If you remember, this was the thickness of the PCB substrate. It was an FR4 material, and I chose a standard 31 mils as the thickness of that PCB material. And the width of that line for getting a 50 ohm standard characteristic impedance was 1.47 millimeter. And these are the other materials of the board and also the copper property. Okay, as long as we have these parameters ready based on the ADS simulation, we can start the HFSS simulation. Okay, let's go to the HFSS. Okay, now we're in HFSS, so I'm going to make a new project. I'm going to change the name of the project into Online Test 1. And then I'm going to click on the HFSS design, and it creates the environment for me. Okay, so now the first step is to create a box and make a substrate. I'm going to make a box like this, and I'm going to change the name of that box into Substrate. I'm going to change the material into FR4, and then you can change the color of that box into something meaningful. I'm going to choose green. Okay, so the next step is to set the size of this box. So if you remember, based on the ADS simulation, the width of the line that we selected was 1.47, and the size of the box should be way larger than this value in order to have enough electric field around that line to have a correct electromagnetic solution for this microstrip line. Okay, so I'm going to select the width of that substrate into, for example, 20 millimeter, so it's wide enough for that microstrip line on it. And then the length of the line, I'm going to select it as 50 millimeter. Okay, so in order to do that, I'm going to select the object, come here on the create box. Because I'm going to put the microstrip line along the x-axis, I'm going to change the x size into 50 millimeter, the y size into 20 millimeters, and then the z size is the thickness of the line, in this case 0.787 millimeter. Okay, and because I want to put the line in this substrate in such a way that it would be right on the along the x-axis, I'm going to change the position of this box into -25. The y position, I'm going to set it to -10. That will be the position of the corner right in the back of this box. So if I hit enter, it goes to the position. So if you take a look at this box from top, you can see that this box is right at the center. So in order to do that, I'm going to right click, go to the view, apply orientation. I'm going to select top, and as you can see here, the box seems to be right on the center of this environment. Okay, so the next step is to create the microstrip line on top of this box. So there is a very useful video, and I'm going to put a link to that video in the description box below. I highly recommend to watch that video. But in order to do that, then we're going to find the cross section of this box with the XZ plane, and if we design the microstrip line on top of the box like that, then everything would be relative to this box. So if you change the size of this box, the size of the microstrip line will change accordingly. Okay, in order to do that, I'm going to select the box. I'm going to go to Modeler, Surface, Section, and I'm going to choose XZ, so it creates the cross section of this box with the XZ plane. And as you can see, this is the cross section. And now I have to change the thickness of this section based on the width of the transmission line that you want to have on top of this box. So I'm going to select this cross section. I'm going to go to Modeler, Surface, Thicken Sheet, and then I have to enter the width of the microstrip line. In this case, 1.47 in millimeter. I'm going to check the both sides, so it would be completely symmetric with respect to the x-axis. So I'm going to hit OK, and it makes another box inside the box that I had at the beginning, as you can see. So now the microstrip line would be the top surface of this box inside the substrate box. So I'm going to select the top surface, and in order to do that I have to change my selection mode from object into faces. You can right click and then hit the second option, and now the top surface of that box is selected. So we have to create another object. So I'm going to go to Modeler, Surface, Create Object from Face, and it creates another object for me that is the top surface of the box inside the substrate box. So I'm going to change the name into Top Metal, and also I'm going to change the color into something coppery, this color. You have to do the same thing for the bottom plane. So I'm going to select the bottom surface, go to Modeler, Surface, Create Object from Face, and I'm going to do the same thing. I'm changing to bottom metal, and now the color into something coppery. Okay, so the next step is to assign the boundary conditions to these two top and bottom metal layers. So in order to do that, I'm going to select the I'm going to select the object, so it selects the top metal. I'm going to right click on it, go to Assign Boundary, Finite Conductivity. I'm going to assign the name to it, Copper Top, and then I'm going to check the Use Material, and I'm going to select the copper. Okay. So I'm going to do the same thing for the bottom layer. Assign Boundary, Finite Conductivity, Copper Bottom, Use Material, and I'm going to select copper. I'm going to hit OK. So now these two materials are already assigned. We have conductors on top and bottom. So the next step is to create the ports, the input and output. Okay, so again we have to select this surface right here at the beginning of the line, but before defining the ports here we have to ensure that the solution type in the HFSS is terminal, because we're going to put a lump port at the beginning of the transmission line. So now I'm going to select the surface, Now I'm going to go to assign excitation, and then I'm going to choose lump port at the beginning, and it assigns like number 1 to this port, and now I have to select the reference plane for that port. I'm going to choose the bottom metal. I'm going to hit OK. We have to do the same thing for the other port, the other side of the transmission line. I'm going to select this. I'm going to assign excitation, lump port. Now I'm going to select the bottom plane again. So now the structure is ready, and now we have to define a box around the entire structure, and that will be the area that HFSS solves all the green functions in it, and that will be total vacuum. In order to make that box, I'm going to click on the box, this icon right here, and I'm going to set the absolute offset. Now I'm going to change it in 50 millimeter from each side of this structure. You can change that if you think that in the simulation process, if it takes a long time, you can change this box property. If it's smaller, then the simulation would be obviously faster. Okay, so it creates another box around the entire structure, and as you can see, and in order to make this box invisible, we can go to this visibility and uncheck this, so basically you don't see that box anymore. Okay, so now we're ready for simulation. Okay, in order to do that, I'm going to go to HFSS Design 1. It has all the parameters of this structure. You can see the boundary conditions that we defined, copper top and bottom excitations. We have defined 2 ports, and if you click on them, it shows where those ports are. And now I'm going to right click on the analysis, add solution type. This solution frequency is the maximum frequency that we want to set the meshing structure of the entire microstrip structure accordingly. If you choose like high frequency, let's say in this case I'm going to choose 6 gigahertz, so it sets the size of the mesh structures based on the 6 gigahertz. So adaptive solution, this would be the number of passes. It's by default 6, and it would be 6 times that we pass this solution. So this would be the maximum delta S, and this would be the 6th time that we pass this criteria. And if the difference between the scattering matrix is always below 2%, and that happens for 6 times, then we can accept that solution as one of the solutions of that green function. And I'm going to select that as a starting point of any simulation. So I'm going to go to the next tab on the options. If you think that you're running out of memory, then you can change this 30% into something smaller, 20%, and it saves some memory on your RAM. So I'm going to show you the other tabs, and basically I think the most important tabs here are general and options. Okay, I'm going to hit OK. Okay, so now I'm going to go to setup, then I'm going to choose add frequency sweep. In the general tab, I'm going to change this into discrete, sweep type into discrete, and now I'm going to simulate the entire structure from 1 to 5 gigahertz with the step of 0.1. And you can also see all the frequency points. If you click on display, it shows you all the frequency points, so it solves all the structure for at each frequency. If you want to see the electric field, magnetic field at the end of the simulation. You can check that. I'm going to hit this, and in the default, I think we don't have anything, and I'm going to hit OK. So I think we are ready for the simulation. Before doing that, I'm going to check all the parameters here. If we click on the validate, it shows that everything is perfectly set and we are ready for simulation. Okay, so I'm going to click on the analysis all, and it does the simulation for us. It takes some time based on the frequency setting. Okay, I'm going to click on that. And as you can see here, it's showing what HFSS is doing on each step. It depends on the size of your structure. This process might take a very long time, and sometimes you will run out of memory, and that's why you have to simulate all your large structures on the server. So as you can see, it starts from 5 gigahertz. Now you're at 4.9 gigahertz, and at each frequency it solves the green function for 6 times to ensure that the delta S is below 2%. Then we're down to 4.8 gigahertz. Okay, I'm going to stop the recording, and then I'm going to show you the end result. Okay, so now the simulation is done, and we can see the results. So in order to see the result, here in this box right here, you can right click on the result. You can choose create terminal solution data, and you can choose rectangular plot, and the first thing we're going to check is the S11, and as you can see, top model S11 in dB. If I click on the new report, it shows me the S11 result is below -30, so it means perfectly matched. And about these jumping up and down, this is because we chose like the discrete, and you can choose like a finer steps in the frequency axis to get rid of all these values. But overall, it shows the trend, and as we expected, we had 2 notches. These notches are because of the length of that transmission line. The other thing that we're going to check is the S21 in order to see the loss in dB. And we can see that 2.4 gigahertz, for example, here we have something around 0.4, half a dB of loss, and that's because the line length is quite long. And the other thing we can check is the S11 on the Smith chart. So I'm going to close this window. I'm going to go to the result, and now I'm going to go on the second option, Smith chart. Now I'm going to select the gamma 1 on the Smith chart. Now I'm going to click on that, and then you can see that we're right at the center, perfectly matched to 50 ohms. So I think that covers the simulation of the line in the HFSS. I'm going to close these things. There's one more thing I want to check here, and that would be the current density in the line. So if you want to see the current density, you can select this transmission line or top surface, and then you can go on the field, plot field on the J. You can choose the magnitude of J surface, and you don't need to do anything here. You can select like different frequencies and phases if you want, but I'm not going to select anything. I'm going to hit done, and as you can see here, it shows the current density on this microstrip structure. And as we expected, at different points, because the line length is more than a quarter wave length line, it has some notches right in the middle, and it shows at these points the current density is very low, so basically 0. These are the notches that we have in this microstrip structure. Okay, so if I go to this icon right here, solution data, then you can select which parameter you want to save the data for. For example, here it's on the S matrix, and you can select to display all frequencies, and it shows all the frequencies from 1 gigahertz all the way to 5 gigahertz. And now you can click on the export matrix data, and you can save this matrix in a folder, so we can use it in different software, for example in ADS. So I'm going to hit save, and it asks if I want to have 15 digits of precision. It's fine for me in 50 ohm reference. I'm going to hit OK, and now I'm going to close this window. So now everything is ready for ADS simulation. So now if I go to the ADS, this was the transmission line that we designed before. So I'm going to increase the length of this line to 50 millimeter. I'm going to change this S parameter into 1 gigahertz. 1 gigahertz from start stop up to 5 gigahertz. Step up 1 megahertz, 100 megahertz. Right. So this would be the transmission line that we designed in ADS. So if I run the simulation one more time, you can see that S11, you should be able to see some notches in the S11 now because the line length is quite long. Okay, yeah, as we can see here, we have different notches, the S11. Alright, so now the next step is to bring that data here so we can compare the results in ADS and HFSS. So in order to do that, you have to bring that S parameter here. So you can go to the data item palette right here, and then you can choose the S port, N port S parameter right here. So I'm going to put it here. Initially, at the beginning, it has like only one port. I'm going to double click on that. I'm going to increase the number of ports into 2. And I can also choose no reference pin for the input and output, or I can choose like single reference pin for each port, or 1 reference pin per port. Okay, so in this case, I'm going to select this. So I'm going to put like 2 different ports at each side. Each side has its own reference point. But it's not important in this case because the reference point of the input and output are the same, so we're going to connect these 2 points to each other. So I'm going to put like 2 ground ports, input and output, and then I'm going to put as parameter port the input and 1 at the output. Alright, so now we have to find that S parameter that we already generated, which was here. Okay, now it's using that S parameter. So now if I simulate the circuit again, this is the previous one. This was the ADS simulation, and now I'm going to select the S33. That would be the S11 of the HFSS result. So this is S33. Add it here in dB, and we can see that there is like some frequency shift between these notches. That is correct. And also we can see that the S11 that we see in the HFSS is a little bit higher, almost like 10 dB higher than what we get in ideal simulation in ADS. So now here S21, so that will be S43 in dB HFSS, and as we expected, the HFSS gives us a higher loss in the line. On the Smith chart, now we're going to see the S33 again, and if I zoom on it, you can see that we have a wider variation at the center, but it's close enough to match. And then I'm going to see the phase of S43 in this case to see how close they are. And they're kind of close to each other. 2.4 gigahertz that we were thinking of, it has very close value to the simulation results that we get in ADS. Okay, that was it for today. I hope you like the video. If you like, please hit the thumbs up button and also subscribe to my channel. Thank you very much, and enjoy the rest of the day. Thank you.